Hi, everyone. Good afternoon. So welcome to day 2 of this workshop. And I think we should continue where we left off yesterday. So just a quick recap. Yesterday, we started learning about how to query entire tables from the DDR. We learned how to limit our output to specific columns or specific rows with the where clause, where we could come up with conditions. And only those rows would appear in our result, which would satisfy the condition. So today we are going to first work with multiple relations. At the same time, we're going to look into some data aggregation and some data grouping inside our data set. And we are going to have a look at subqueries, which is a very handy element in SQL language. So with that in mind, let's get into it. So our first topic will be talking about multiple relations. And you might remember this table from yesterday, the patient's table. So this is the same. We have an ID for each patient. We have first names, last names, date of birth, and sex. And now we have a new table, an encounters table. This is also sort of a mock relation, which is supposed to look a little bit like the CDM encounter fact table. Just one example how it is different. In the DDR, we do not have patient complaints. Okay, in the identified data set we do, but unfortunately in the DDR we don't, because that would probably help identifying patients. So for the encounters, we have an ID for the encounter. We have an ID for the patient who has the encounter. We have a date when the encounter occurred. We have the facility of the encounter, and we have a complaint field for this. Okay, and as we talked about it yesterday, all the patients have an ID, and all the patients are referenced in the encounters table. And yesterday we talked about what keys are. So in this case, what would be the keys? The identifiers of the individual rows. So first, for the patients table, which one can we consider as to be a key, which will uniquely identify a patient? Exactly, that would be the ID. And what's the key in the encounters table? Yeah, actually both are keys. So the ID identifies one encounter, and the patient ID in this case is called, and this is a new term, a foreign key. The foreign key means that this is a key in a different table. So it's shown in this table, but as you can see, the same values can appear several times because, for example, let's look at Ann Smith, who appears twice in the encounters table. But it's not counterintuitive because Ann can have several encounters. Okay, but the encounter IDs for both of her encounters are unique. So we can identify her first encounter by the ID field in the encounters table, or we can identify the second one. Okay, so the new term here is the foreign key. And we will work a lot with these. Okay, so we have patients and encounters. So how do we list the names and the date of birth of patients with some kind of pain as the complaint? What is the added difficulty compared to yesterday? So remember, what's the first step in solving such a question or such a problem? That's fine. So the question is, here we have two tables. We have the patients and the encounters table, and we want to see the names and the date of birth of patients who had some kind of pain as a complaint. We can also start with that. So yesterday we talked about that the first step, usually when we have a question like this, is identifying the tables which contain the information we need. So here we see that we will need names and date of birth.
You need the encounter table. Oh, you need both tables.
Exactly.
Date of birth is the patient table and encounter table. That's the complaint that you're looking for.
Precisely. So that's the difficulty compared to yesterday's queries, because yesterday all of our queries operated on a single relation. And this time we somehow have to find some kind of connection between the two tables, pull them both, and extract some data from this combination.
This is between the two circles, or what do you add?
No, There was something else, which doesn't mean that I won't be drawing circles for this one too. So there are different kinds of ways to join two relations, two or more relations. The first one is called a cross join, or direct join, or Cartesian join. As you might also remember, one of my agenda is to confuse you with all the equivalent terms. So these three are equivalent in this context. Who remembers the Cartesian product of sets from maybe discrete mathematics class or something similar? And now comes the join part. So let's say we have two sets. In one set, we have A and B. Let's call this set 1. And in set 2, don't worry, this is the most math we will have on this class, probably. And in set 2, we have 1 and 2 and 3. What would be the direct product or the Cartesian product of these two sets? Then I will help. So basically, the way we create the Cartesian product is we take all the elements from the first set and pair it up with all the elements in the second set. Okay, so an S1 cross S2 would be this. So Eloy asked me not to draw too low. This is S1 cross S2. And what we will have here are A1, A2, A3, and the same, B1, B2, and B3. Okay? So the cross product of two sets is joining every element in one of the sets with every element of the other set. This is the Cartesian product. So we have this, and we also know that we can think of all the relations or tables as sets. Or to be more precise, sometimes multi-sets. So this part is very important in this case because it means that if we consider relations to be sets, we can actually we can understand what the Cartesian product of two relations would be. So this is how the syntax in SQL looks like. What is probably familiar to you is select a list of attributes from, and yesterday we only put one relation every time after the from. But now we know that we can put a list of relations. For example, in this case, select star, right? Star is a placeholder for all the available columns. So select star from patients, comma, encounters. So if we join two relations like this in the from clause with a comma, what it means in the background is that we are creating the Cartesian product of the two relations. So how would this look like? Well, we take the first row from the patients, which was Anne Smith's record, and we take the first row from the encounters table. We basically stack them together, and we have the first row of the product. Then we are going to use the same row from the patients table, Anne Smith, and we're gonna match her up with all the encounters. Okay, and then what we're gonna do is we're gonna do the same thing for the other two records in the patients. Okay, so we're gonna match up Michael and Lucy as well with all the available encounters. So now what we have is a big table. It's an 18 times 10 table. What's the issue with this? Exactly. So what would the first row here mean? Because we talked about that every row represents an entity. It's an object with all its attributes stored in a table. So what does the first row here mean? What's the entity behind it? Right, in patients, the entity behind one row was a person, a patient. In the encounters table, the entity behind it was an encounter. And what's the entity here? And I don't mean the idea. Sorry?
Is there a link now?
Mm-hmm.
So isn't it one patient will encounter.
Yes. So if you look at the first row, specifically the first row, 3006 Smith, N April 6, 1986, F 91 132, 3008, 7, and January 24th, 2020, Ronald Reagan and ear pain. What does this row represent? Let's try it with the, sorry?
It's an encounter for that specific patient
Which patients?
and Smith.
You would be correct if it was for the second row. I will have a little.
First,
Mhm.
right?
Yeah, so for the second row, you are correct. The entity behind that is an encounter for Ann Smith. I will help you the first one, it makes no sense. Okay, we are joining a patient with an encounter, which is somebody else's encounter. So we have to take care of this because what do we do with that data row? Sorry?
How do you know that's not the answer?
How do we know? Exactly.
Oh, but then row 3 is incorrect.
Okay, so actually let's go row by row. So the first one is incorrect, and the second one is, third one, the next one, and so on and so forth. So that is a disaster. So how would you undo this disaster? And this is something which we actually learned yesterday. Let's say this is your table, what you have, and all you want to keep is the meaningful data, the meaningful rows. How do you filter rows? What's the clause? What's the keyword? What we use to filter rows? Is it select? This one I'm not gonna say. Where? Thank you. This is a where. So how would you phrase the where condition here to keep only the relevant rows? Very good. Where patients.id equals to encounters.patient.id. One thing which I might not have said yesterday is here you can see that we have two tables and both tables have an ID field. So it's called the same, but it contains different ID. In the patients table, we have patient IDs. In the encounters table, we have encounter IDs. So to avoid ambiguity, what we do is we refer to the column as the originating relation dot and the column name. So here we have patients.id and we have encounters.id. Okay. So we have multiple relations with similar column names or same matching column names. This is how we unambiguously refer to one of those. So yes, how do we keep only the relevant rows of the product? And you were correct. We have to check whether the patients.id equals the patient ID. So far, so good. Okay, here I try to show with the red where it does not match and with the green where it does match. So after this, we will be left with, actually, yeah, let's go into more details. So remember the original question was, let's list those patient names and date of birth where they presented some kind of pain. So this is a query which operates on both tables. It looks like, so you're familiar with the select clause. From select, so in the select clause, we select the last name, the first name, and the date of birth from the patient's table. But we are only interested in those patients where the complaint field contains pain. And this is a new SQL element. Yesterday, we checked a string where it equals to something. Here, we use something which is called like. And the like keyword is a string pattern matching, basically. We don't check whether complaint is exactly the pattern what comes after. We check whether it fits the pattern. Here, the pattern means that the percentage sign can replace 0, 1, or an arbitrary number of characters. But what we are looking for is pain. So something can be in front of pain, something can be after pain, but what we need in the complaint field is pain. So every, sorry? Yes, exactly, it's a white character. So this is how we check whether pain is contained in the string in the complaint field. Let's look one by one. So as you remember, I mentioned that it's always helpful to think about the order of evaluation. So what happens first is that the tables of interest are loaded. So here the from patients encounters results in this big table with the 18 rows with many unnecessary rows as well. Then we do the filtering. First, we check whether patient ID equals encounters.patient ID. So now we only have those rows. And now we check the other condition, complaint like pain. So far, so good. Anytime, let me know if we're going too fast or too slow, and I try to adjust pace. So here we have 3 rows left. Any issue with this so far? What do you see? What is going to happen in the next step? Okay, first, which one is the next step? Sorry? In the next step. So the next step will be evaluating the select statement. How many rows will we have after the select statement? What do you think? Sorry? Mm-hmm. So both rows will appear, yes, and also the third one, because that also fits the query. So we will have 3 rows. How many columns? 3 columns, correct. So how many different rows will we have? Yes, 2. Okay. So how do we make, because you see that now we do have a duplicate. How do we take care of this? This might also be a new keyword, and it's called distinct. If you put distinct after the select keyword, then you will get the resulting query, and you will only keep one element of all the resulting elements in the resulting query. You might want to pay attention to that. Had we left the date of the encounter in the results, then we would have 3 different rows. But since we are only considering these 3 columns, now there are no more differences between the first 2. So with the distinct, we only keep the different names. And this is how to solve this question. How do we list the names and date of birth of patients with some kind of pain as the complaint? So here, the way we did it is basically we took all the records from one, all the records from the other one, we meshed them up with each other, and then we used a where statement to only filter out the ones which are relevant to us. So this is one way of joining 2 tables. Luckily, there are more convenient ways. One is called the conditional or inner or theta join. I think mathematicians use theta, and probably database experts use inner, so I like using conditional. This is how it looks like. Select a list of attributes. Remember, the attributes can be any attribute from the first or the second relation, but if there's any ambiguity between the 2 columns with the same names, you need to specify which one you mean. Unless you use star, because then you will just get all the available columns. And then what you do is you say from relation 1, inner join relation 2 on, and then you put a condition there. And this condition is a very similar one than the one after the where clause. So whatever condition you want to put after the where clause, you can put this after the on clause. You can think of it as a shorthand, which is more easily readable. Yesterday, I tried to make a point of how SQL is great because it almost reads like an English sentence when you read a query. And I think this helps this aspect a lot. So let's look at a specific example. Select star from patients, inner join encounters on patient.id equals encounters.patient.id. So you can see that this is exactly the same as the where. It's just more readable. If you just glance at it, you will immediately see what the relationship is between the two tables in the from clause, which makes the whole query very readable. We've been working with pretty short queries so far. I've had to write queries which were 150 rows long. So readability does matter. So let's look at the specific example. Here we have the big table. Sorry, we do not have the big table now because we already joined them based on the condition. Who remembers from yesterday, how do we sort an output? Order by, correct. So let's view them in chronological order. What will be the last row of the query? Order by date. Okay, this is something which we actually did yesterday. Maybe one note is that it's not an important note. I will not confuse anyone. So these were two kinds of joins, the Cartesian join and the inner join. Now let's look at two very interesting kind of joins, the left join and the right join. So in order to demonstrate this, I would like to remove one row from the patients. So let's remove Lucy Green. And from the encounters, let's remove both encounters of Anne Smith. You might remember the example from yesterday with the friendships, where there was an inconsistency in the table because if we removed all the friendships of a person, we lost all the remaining information of that person, such as first name, last name, and date of birth. Here, it cannot happen because we have a patients table and an encounters table. But what can happen is that there might be information in the encounters table regarding a patient, which is for some reason not in the other patient table. So what happens here when we try to pull data from both sides? That's where left and right joins come in. So these are the new tables. Again, remember, patients, now we have only two patients, and the encounters will contain an encounter for a patient who does not appear, and also there is a patient who does not have any encounters stored, okay? So now there are rows in both tables which do not match up with anything on the other side. So if we do select star from patients and encounters, if we do this cross join, we get this, right? We have 2 rows on the left, we have 4 on the right. So we know that we will have 8 here, 2 times 4, because we will match up everything with everything. Then we add the where statement, and then we will get this. These will be our relevant rows. This is if we use the cross product or the cross join. If we use a conditional, then we get exactly the same. Okay, so it's important that now we have different outputs because there are some patients without encounters and encounters without corresponding patients, and they do not appear in the result. There's only a single patient appearing in the result. So I guess it works out well if we want to find data on patients who had encounters. How does it work if we want to see how many patients a hospital has on record and what was maybe the average number of encounters a patient had at the hospital? If we only look at the patients who have encounters, who match up with something in the encounters table, then we can lose a lot of information. For example, we would be losing all the patients who had 0 encounters in a specific year. So how do we address that so that in the result, we will have all those information as well, or some of the information as well, which did not match up with anything on the other side, but we still don't create bogus information. So that's where left and right joins come in. because we left join. And here it's important to note that patients is on the left side. Okay, so left join will look like, first, will N Smith be paired up with anything? No, there's no corresponding encounter. But still, we don't want to lose N as being part of the data set. So this is what happens if we do a left join for a row which does not match up with anything. It's called a dangling row or dangling tuple. And all the fields from the other table will be filled with nulls. You remember null is an indicator of missing or not applicable data. It's not zeros, it's not empty strings, it's null, which means that it is missing. Here in this case, it means that we just created a table where we matched up patients with encounters. And since N did not have any encounters, all the corresponding encounter data has to be null because it's not applicable. It's not missing, it's just not applicable. She hasn't had any encounters. You probably have a good idea of what's going to happen if we do a right join. First of all, will N Smith be part of the resulting relation? Good answer, no. How about the encounters of Lucy? Will they be part of the resulting relation? So she would not be in it, but her encounters are. Okay, and then we would get nulls for all the fields in the patient relation. The reason is that we found a relation with a patient identifier, which is just not present in the patient's table. Therefore, we don't want to lose, because let's say that we are doing this, we're creating this table to count the patients who came in with some kind of pain. For some reason, Lucy might not be part of the data set. Let's say that Lucy went to a different hospital and maybe she opted for her data to be removed from our database. And so now we don't have that, but we still want to know how many patients visited with a complaint of pain. If we remove that too, then we will lose valuable information when we maybe want to estimate the amount of painkillers physicians will be prescribing the next year or something similar. Okay. This way, although we were missing the patient data, we still have the encounter data in the result. Okay. Here on the left side, the nulls are not applicable. In this case, they are in fact missing. So these are two examples of when we use nulls. And with the full join, what's going to happen? Any ideas? Precisely. We're not going to discard any of the dangling tuples. We're going to keep all of them and just fill out nulls for everything which we don't have. I know it's a lot to digest, but does it make sense? Basically, different ways we want to pair up tuples from different tables, always depending on the context and what we want to do with the data. Which brings us to exercise 5. Okay, so we arrived to grouping and aggregation. Let's get back our original tables. So we've put Lucy Green back to the patients, and we put N's encounters back to the encounters table. So how many patients are present in the patients and the encounters table? So by looking at it, it's pretty clear. The patient contains 3, encounters also contains 3. So how do we actually count it? How do we count rows or values? In SQL, it usually reads as English, so we're going to use the keyword count. So count is a function which will aggregate results. If we just say select star from patients, we get the original table. Everything changes when we say count. By count, we turn the output So we reduce the dimensionality of the output. We basically aggregate rows. So when I'm saying select count star, and I put anything else in the body of the query, then it will count the number of rows in the output. Okay. Here we see that select count star from patients gives us a result of 3 because there are 3 rows in the table, and for encounters, the output is 6 because there are 6 rows in the output. Okay, so again, with the star, it just gives you the table. Count star gives you the number of rows. Another question, how many facilities are present in the encounters table? Okay, by just looking at it, how many are there? 2, Ronald Reagan and Santa Monica. How do we count it with SQL? So what if we do this? Select count facility from encounters. So what happened here? What did we count? Yes, number of rows, or in other words, because it's just one field, the number of values. Are we interested in the number of values? We are interested in the number of distinct values. And this takes us to the distinct keyword, which we used yesterday. Select count distinct facility from encounters, and this will give us 2. Okay, so this is also another way of using the count aggregator function. How many? Sorry? Exactly, it will be 6. How many encounters are present at each facility in the encounters table? So what if we do count again? We won't be able to distinguish between different facilities. So what we have to do is that we have to form groups of rows based on something which is common in them. So it's clear that we can actually aggregate them or create groups based on a couple of things. We can group them by patient ID. And then what would we get? How many groups would we get if we just took different groups of rows where in one group the patient ID is the same for all row? What would be the meaning of those groups? Encounters of the same patient. Yes. So we would get how many groups? 3. 3 groups or 3 patients. If we group by facility, how many groups do we get? 2. So these would be the 2 groups. If we just look at it like this, it's pretty easy to see that there are 3 encounters in both groups, but how do we translate that to SQL? The syntax looks like this. We do select facility and count star as count, just to give a name to the column, from encounters, and everything changes when we say group by. Because so far, everything what we have been doing, select, the where, so these conditions, they operated on rows. But once we say group by something, here group by facility, we do no longer have single rows. Now we have groups. And it's very different how we deal with groups. For example, let's say we have a patient. Can we display the date of the encounter for the first row? So we just have the first row. It's the complaint was ear pain. Can we find the date for the specific encounter? What's the date of the first encounter in this table? Yes, so we can specify we can find the exact date. But what if we don't look at one row? What if we look at all the encounters for patient 3007? So we have 3 of these, right? We have one January, one in November, and another one in next January. So what if we have a group of all the encounters for patient 3007? What's the date of this group? 3 different dates. So what is the date of this group? The question doesn't make sense. The group does not have a date. So when we are querying groups, when we are dealing with groups, it's very important never to forget that we cannot ask for individual attributes, only group level attributes. What would be a group level attribute in this case? So we have two groups. What's a group level attribute? Sorry? Sorry, I can't hear. I can't hear. Thank you, so yeah, facility, correct. So that's sort of the trivial group attribute, exactly, because that's how we form the groups. What else? What else can we ask about these groups? Again? Not really, because several patients can visit the same facility. What kind of complaints? So you mean like sort of an aggregate thing to list all the complaints which occur in this? Perfect. But by the way, the first one was also correct. So you can actually take a group, you can take the complaints, and you can concatenate the complaints after one another to have a list of complaints. Is that an attribute of the facility? Of course it is. What complaints did people arrive with to this facility? That's a valid question to ask about a group. Another example would be the number of elements in the group. Another thing could be the average age of the patients in that group. Just always keep in mind, if you want to query attributes of a group, you will probably make the mistake, but realize it when you make the mistake when you're trying to ask for an individual attribute from a group. SQL will give you an error message, so you can trust in that. But this is something to keep in mind. Groups are different than individual rows. And when we issue group by, then we change the nature of our data. So now we have groups. So is this syntax clear? Again, the evaluation, I will show you the evaluation, and I think it will make it much easier. To keep in mind, there are many aggregator functions, just a few examples: sum, average, mean, max. These operate on numeric fields. So for example, let's say I want to know the sum of the patient's ages in a facility, then I can put sum instead of count. And I'm not going to count the encounters in a facility. I am going to sum up, and then I would, instead of the star, I would put maybe patient age. Then I would put up the patient ages, sum up the patient ages. Or if I use average, I can look at the average age of patients who visited a facility. Mean, max, similarly, and there are different aggregator functions for different data types. For example, concatenation for strings. If you wanted to generate the list of complaints, then you have a concat function. Not sure if it's concat or concatenate in this SQL version, but you can look it up. Okay, so here, if we issue this query, this is the output we get. One row for facility. Again, facility is a group level attribute, and the number of encounters at the facility is also a group level attribute. So which facilities have multiple encounters? How would you approach this? First of all, which table is closer to the answer? First one or the second one? Yeah, the second one, because it already contains the number of encounters in a facility. So if you want to find facilities with multiple encounters, what do you have to check? Count is larger than one. How do we usually do that? How do we filter rows? What is a keyword? Where? Although now we are dealing with groups. And as I said, everything is different with groups. So with groups, it's not where. With groups, it's having. For whatever reason, it's called having. Okay? So select facility and count star is count from encounters. Group by facility, having count star greater than one. Actually, one question. Do you remember from the evaluation? So what do you think? why don't I just put having C and T greater than 1? Seems like I'm just typing functions for no good reason. Exactly. First, we evaluate the from part. So we are loading in the background. You can imagine that the from part gets evaluated the first. We're loading the table. Then we are grouping by facility. Then we are limiting the rows to those where the count star is greater than 1. And only as a last step do we evaluate the select statement. And since count is the name which we gave the count star column, it happened after we after we limited the output rows with the having clause. Okay, so since we created the C and T in the select, and the select gets evaluated for the last time, we cannot use that in the having. This is also a very common mistake people make. So the next topic is subqueries, which is another interesting element of the SQL. So let's list the patients who had encounters at the facility with the most encounters. Does the question make any sense? So list the patients who had encounters at the facility with the most encounters. So we have multiple facilities with multiple number of encounters. We select the facility which had the most encounters, and then we just want to list those patients. Okay. So how would we do that? We have this patients and encounters table. How would you do that? What would be the strategy? Very good. First step is finding which had the most encounters. In order to know which facility had the most encounters, what extra information do you need, which is not specifically here, but you cannot see just by looking at it in a second? Exactly, exactly. The specific numbers, right? It would be so much easier if you already had a table where you have the facility and the number of encounters next to it, right? It would be almost trivial. So let's try to do that. Let's start from a previous query. So we do select facility and count star as count from encounters group by facility. If you remember, that gave us the numbers, right? This was which query? This one. See on the right, you have the facility and you have the count next to it. So this is the table what we need. So we create it. We order by count. Here, both are 3, but you can imagine that we order it by count in a descending order. So we have the facility with the highest number of encounters on the top, and we select the top one. Does this strategy make sense? Okay, so for each facility, I'm getting the count, and then I order this table by counts in a descending order. So the one with the most encounters will be on the top, and then I'm just taking top one. Okay, so this is how it would look like. First, we evaluate from encounters. Then we group by facilities. Then we select the facility, order by count, descending order. Again, you can see that I'm not naming this variable. I'm using count star, and I select the top one. In this case, we have 3 for both. Okay, so here we are not taking the facility with the most encounters. We are taking a facility with the most encounters. You can imagine a real life scenario where we don't have 3 encounters, but a couple of 100,000 or millions. It's easy to see an order. So we take the top one, which in this case is RMC, probably because R is before S, the alphabet, and then we have the facility with the most case counts, the most encounter counts. So this was the first step. So now we have basically these two. Again, the question was, let's list the patients who had encounters at the facility with the most encounters. So we have the facility, we have the original encounters. So what do we do? What's the next step? So the next step is really just using our original where clause. Okay, because now it's pretty easy. We have that RMC is the facility we are looking for. We just have to check for those encounters which happened in Ronald Reagan. Okay, so select distinct patient ID from encounters where facility equals RMC. Okay. Now there's one issue with this. Let's say that I want to use this query over and over again. What happens if the facility changes? So maybe a couple of weeks from now, the facility with the most encounters is a different one. So it doesn't make a lot of sense that I queried RMC and then I keep this result and I'm just going to run the same query with the same literal, the same RMC. So it's better if I incorporate getting the facility with the highest encounter count into the query. And so this is where subqueries come in. If you remember the set examples from yesterday, you remember that we generated the intersection or the union or the difference between two sets by defining one set inside parentheses, intersect, and another one inside parentheses. I didn't say it yesterday, but those were two subqueries. So the big query, what we had was the first query intersect the second query, but we actually already had two subqueries inside, okay? So this is again the same. When we are trying to equate facility, which is a string, to RRMC, we can replace RRMC with a query, which will have a single string output. As I said, we have relations, we write queries on relations, and the outputs of queries on relations will be also relations. In this case, the relation, the table, what we have on the right-hand side has one row and one column. It's still a relation. And since it has only one value, we can put that after the equation sign. And this will always give us the actual result, okay? So result of this will be this table. You see that we have 3 rows, 1 column, we have the same patient ID, so we will just put the distinct in it again. And there we have the super long list of patients who had encounters at the facility with the most encounters. Again, this is a toy example. This is why we only have 1 patient here, and this 1 patient actually had 3 encounters in Ronald Reagan, okay? So this is why we have the most encounters. Last step, because we were asking for the patient details, is to join up this one with the patient's table, which looks like this. So what we already had here was from encounters. What we modify in this is that we put the inner join patients P on E.patient ID equals P.ID. So we basically just take the patient's table and we stick it next to it. And then we do the subquery, we evaluate the subquery, filter the rows based on this. And then this is maybe again a new element which you haven't used this way. If you want to select all the columns from a specific relation in the select statement, you can do select relation point star. Here, all the columns in the patients table will be displayed because we set patients.star and not encounters.star, or not simply star. Simply star would give us all the columns from both the patients and the encounters table. Here we get only the patients table columns. We apply the distinct, and there we have the patient data for the patients who had encounters at the facility with the most encounters. Sorry? Yes, and I'm not sure why I didn't. I will actually modify the slide. Good catch. Yes, the reason for that is, so actually you can answer it. When is the P symbol created? In which clause? In the join, which is part of the from clause. And since that gets evaluated before the select statement, you can use it in the select statement. So these were subqueries, and the cousins of subqueries are temporary tables. I'm going to show you the solution for the exact same question, but using a different query writing strategy. So let's look at temporary tables. Question is the same, and on the right, you already have selected the top one facility. So let me introduce you to a different kind of notation, which would be this one. What I'm doing here is I'm saying with max f as, and then I put a subquery there. And what I'm essentially doing here is I'm defining a relation with this query, and then I'm naming it. I'm giving it a name. It's max f. From now on, as long as this single query lasts, it works as a complete relation. As I can say from patients, from encounters, I can say from max f. Now it's a table. Why is it a temporary table? Why is it temporary? Exactly. Once this query has finished running, we will still have the encounters table. We will still have the patients table, but we will no longer have the max f table. We have the max f table right until the closing semicolon, and then it's gone from memory. It's a temporary table. We create it, we use it, and then we throw it away. Okay? So here I define max f as this relation, this one row, one column relation, and then I'm using it. Select distinct patient ID from encounters, inner join max f on encounters.facility equals max f.facility. So I'm basically creating a join, and I'm only keeping those facilities which are the same as the only facility in the facility table. Right. I only have to look at this after I generated the top one facility. Keeping these rows, and then evaluating these. Keeping only the patient ID and only one of each. So now we have the patient ID. So now what we are going to do, because first we needed the facility with the most encounters, and now we need the patients from that facility. So now we are creating another temporary table for these patient IDs. I usually call patient IDs as PIDs. So if you ever need to write some query and you email me and I send you some example queries for something, then PID always refers to patient ID, and EID always refer to encounter ID. And I suggest that you also find easily rememberable and very short names for these if you use them frequently. So now we have two temporary tables. We have the max F and we have the PIDs. So for our real query, or I would say our core query, we can say select patients.star from PIDs, inner join patients, on PIDs.patient ID equals patients.id. Again, I could have used, oh no, here I didn't use the P for patients, so patients.star is appropriate. If you think about it, it is a very different strategy. So my favorite way of using this is if I get a request, I should pull some data, and it's very high level, like here. We need to do several steps to get to what we're actually interested in. So my strategy is usually I think of how would the table look like, which I wish I had to solve this task very easily. Oh, I wish I had the table with this and this column and already calculated values. Oh, that would be awesome. So I write the query for this. Oh, but I don't have this table. So then I start writing that table. And if I bump into any issues, like I still don't have some value which would be very handy for that temporary table, I treat it as if I already had it, and then I will start working on another temporary table. So This might not always be the most efficient way of writing queries, but it is very efficient if designing the query is a complex task. It is also pretty readable. I mean, now I look at it and it's like 3 paragraphs of code, but actually the first one deals with finding just the facility with the most encounters. The second one only cares about gathering the relevant patient IDs. And the third one actually solves the task. So I guess it's to everyone's own taste whether this one is more readable or this one. This is more compact, lower number of rows, and this one is completely different. I don't always use the same strategy myself, so I just want to introduce you to the usage of subqueries and temporary tables. So here we evaluate the last one. Sorry, I forgot this one. And the last step will be to get rid of the ID column, which is still coming from the encounters. And there we have the result, same result as before, but with a different strategy. So to give like a super brief SQL summary, when it comes to the level of a query or a subquery, the order of the keywords or the clauses inside the query is very important, and you cannot mix them up. Always starts with select, from, where, group by, having, and order by. If you have a subquery, then of course you can, so for example, if you have a subquery after the from clause, because you are creating a table and you are already querying from it, then you can also have select, from, where, group by, having, order by inside the subquery. Okay, so on the highest level, these are the clauses of a SQL query. Which brings us to exercise 7. I think we at most we'll have time for one, but let's give it a try. So display the number of patients who were discharged to prison, jail, or law enforcement in the past year. I thought it was a fun one. So again, try to be creative, try to find the tables which contain the relevant information, try to find the columns inside those tables which you will need, find out how will you connect tables, but above all, try to figure out what the subtasks are of this one to make your life easier. Yeah, so my apologies for not having enough time today to go over all of this together, but we will do so on Friday. So tomorrow, Lingyu is going to teach, and he will talk about the Atlas database and how it is connected to the DDR, how you can query it, and he will show a bunch of interesting stuff. And I'll also be here. And on Friday, we will go forward with this first, and then we are going to touch a couple of real-life queries, which we actually had to write, pulling different patient cohorts. I think that's going to be pretty interesting. And also it will show you a lot of details of the database so that you can then start designing your own real-life queries as well. So with that, second day has concluded. I'm happy you all joined. So see you tomorrow and hopefully after tomorrow.